Okay, let's do a gravitation problem. So this is going to be a gravitation. Okay, so gravitation problem. Okay, and here we go. Let's say we have a star, a neutron star. So let's draw our star here. This would be your neutron star. And we have here the center where you got all the mass. Here is where you have all the mass of the star concentrated. And you have a radius right here, the radius to the surface. And you have a particle here, a little particle of mass m. And this is a neutron star. Neutron star. And it's rotating. It's rotating around an axis. It has angular velocity. It's rotating, and the question is the rotation is 1 revolution per second, so it's going to be 2 pi per second. That's the angular velocity of this star. It's rotating, and it has a radius. This is the radius, and the radius is going to be 20 kilometers. 20 kilometers of radius. And the question is, what must be its mass so that an object on the surface will be attracted to the star and not thrown off by rapid rotation? So you got an object here of mass little m. And if the star is rotating, you want the object to be attracted to the center of the star and not to be thrown away because of the rotation. So what do we have? Let's see. So let's do a body diagram right here of the situation. And we have all the mass concentrated right here, the big mass of the star. And then you got your little m over here. And there's a force of attraction this way. Let's call it centripetal force. Has to be equal to the gravitational force. So this has to happen. So there must be a force here that is attracting the particle of mass m towards the center where you have all the mass concentrated, all the mass of the star concentrated. And we have that the force, the centripetal force has to be equal to the gravitational force. And the centripetal force is going to be little m, v to the square over r. And that's going to be equal to the constant of gravitation, the mass of the star, times the mass of the little particle over r to the square. So the velocity, the linear velocity is related to the angular velocity with this formula. This formula relates linear velocity and angular velocity. This would be the angular velocity. Angular velocity. This would be the radius. Radius. And this is the linear velocity. This one is the linear velocity right there. So we got that the mass times the velocity is going to be r omega to the square over r is equal to the constant of gravitation, mass of the star, mass of the particle on the surface. You got here the surface, and you got a little particle there, and you want it to be attracted to the center and not thrown away as the star is rotating at an angular velocity of 2 pi per second, which is 1 revolution per second. 1 revolution. This is 1 rev per second. So, and then you got r to the square. So what can we cancel here? Let me see. So this mass cancels with this mass. This is square cancels with this guy over here. And you got r to the square, omega to the square is equal to g mass of the star over r. So you're going to have r to the 3rd power, omega to the square over g is going to be equal to the mass of the star. And that's going to be, the radius is going to be 20 times 10 to the 3rd power meters. And the angular velocity is going to be 2 pi radians per second. Radians per second to the square divided by 6.67 times 10 to the minus 11 Newton meters to the square over kilograms to the square. And if you do all this math right there, you're going to get here that the answer is going to be 4.7 times 10 to the 24 kilograms. And that would be the answer from the book. This is from the Holiday and Resnick Gravitation chapter. And this is the answer from the book. So this one is to the 3rd power right here, right there, to the 3rd power, because look at this one. And there you go, 4.7 times 10 to the 24 kilograms. If you check the units, they're going to check out, because you have here, what do we have? We have meters to the 3rd power right here, meters to the 3rd power. Radians don't count, and then you got seconds to the square over Newton, which is kilogram, meter over second square, that's the Newton. And then you got meters to the square, and then you got more kilograms over here. Meter, and then you got all this is over kilogram. So to the square. So this one cancels with the square. This guy cancels with this one. Meters times meters to the 3rd power. All these cancel with this one, and this one goes upstairs. The kilogram goes over here. This kilogram, because it's going to be 1 over 1 over 1 over kilogram. So he goes up here to kilogram. And there you go. Your units check. Everything is okay. And there you go. You got a problem here from Holiday and Resnick chapter Gravitation. And the answer is 4.7 times 10 to the 24 kilograms. And that must be the mass of your neutron star, which is rotating. And that would be the mass in order for the particle of mass little m will be attracted to the center, where you have the concentration of all the mass of your neutron star. Thank you, and we'll do more problems related to gravitation.